It is, Unit 12.
I have no idea if I'm really recording this. Oh, look at him.
I feel like that's how all the recordings start.
What'd you say?
It's always like, I don't know if I'm recording. Oh, I am. Look at that, I pressed the button. I know it's always in the video whenever I watch it.
It's always in the video?
I swear it always is.
That's because you got an old guy doing this stuff. All right. Some days. Hey, someone hung their clothes over my Galaxy. Sheesh. Oh, man. Okay. Now, in the last unit, we said that if you've got a conductor, if you have metal, you cannot have an electric field passing through it. Electric field lines can't go through it. Otherwise, current will begin to flow in that piece of metal, and a piece of metal just hanging there by itself, isolated, not connected to a source of energy, can't just, create energy sitting there by itself. That means every little piece of metal in the room is a little reactor busily making energy, and that would probably not be true. But if you have a piece of metal and you create a potential difference across it by connecting it, say, to a battery or some other source of electromotive force, a solar cell or a generator, or in our case, a battery, then you could create an electric field in the metal that stays in the metal and causes electrons to move from place to place. And that's an electric current. So I hope I didn't leave you with the impression that you can't have an E field in a piece of metal. You just can't have an E field, a non-zero E field in a piece of metal that's isolated, that's not attached to any source of energy. But once we attach it to a source of energy, we can use the conductor to make electrons flow all we want. But as soon as we remove the battery, the electrons will stop flowing and the E field will disappear. Okay? So, this first part deals mostly with chapter 26, and it's called current and resistance. So the whole unit is called electric circuits. You're fine, Lucas. And this first part from chapter 24, current and resistance. I'm sorry, it is chapter 26. I'll say it. We took care of chapter 24. Okay? We have 3 units left, including this one. Is that hard to believe? After today, you have 3 tests to take. And you were there. All right. So, current. Variable for current is alternatively capital I or lowercase I. Your book uses lowercase I quite a bit, but they'll both be current. What's current?
Current events.
Current events. We actually did this earlier in the year. We needed it for another unit.
Isn't that the rate of flow?
Rate of flow of charge through a circuit. Yep. Okay. I will say rate of flow of charge past a fixed point. Okay, the units are coulombs per second. And the dead white scientist is? Ampere.
He's like crawling around back there. He's like, I'm so sick.
Okay. Now, it turns out that this dead white scientist, Ampere, oftentimes has his name shortened to amp. So if you look at just about anything, current is measured in amps. But the official title of this unit is the ampere. So if you want an electrician to laugh at you, say, you know, I think there's about 2 amperes running through that circuit. Sounds a little frou-frou, right? No, it's 2 amps, man. Hook up your meter, check it out. Okay. The equation dq dt. Since we live in calculus land, we might as well say it that way. Okay, so we've got this wire. It's a chunk of copper usually, but it can be other metals as well. And we have charges flowing through it. Now this is, once again, where Ben Franklin kind of messed us up. For a long time, we thought they were positive charges moving from one point of the wire to the other, when in fact it was negative charges moving in the opposite direction. So we've got kind of 2 ways of thinking about current. One is the flow of electrons through the wire. That's actual current, real current. And then we've got conventional current. We can think of it as positive charges flowing in the opposite direction, whatever those little guys may be. Now, your book and the AP test follows conventional current. Okay? It's traditional, and in physics we never change anything. So they set everything up as if it were positive charges moving from the positive side of the battery to the negative side of the battery, when we know full well that it's electrons moving from the negative side of the battery to the positive side, that the flow is actually in the opposite direction. Every now and then they'll switch to electron flow just for a problem, and then they'll switch back. Okay? So I would not be the only one to find that slightly annoying, but that's the way it is. Now, one way to look at this positive charge problem, one way to rationalize it, is to think of it this way. What if the electrons were like marbles in a tube? So I've got some marbles here. And these marbles flow this way. So as the marbles flow, this marble here moves forward 1, and all these marbles are electrons, so they're all negative. When this marble flows forward, the gap here moves backwards. So if we're living in a negative world, all these guys are negative, a gap in the negativity seems to us like a positive. And so you can think of this in 2 ways. You can think of it as the electrons flowing to the right, or these positive gaps flowing to the left as these marbles move forward to fill up the gap one by one. Well, it's like the tube is standing still, but the marbles are flowing through the tube. And as they pop forward, one by one, they leave positive gaps, which are actually moving in the other direction. Does that make any sense? So it's kind of the gap theory of current flow, and it is just a way of saving the conventional current, that it's positive moving this way rather than negatives moving the other way. Mentally, I kind of prefer thinking about electrons moving from place to place, because I know in my heart that that's really what's happening. But in our equations, we'll deal with it as positive flow. Okay, so next thing. There we go. Look at that. So a space heater in your college dorm draws 4 amps of current. How many electrons pass through its heating element in 1 minute? Okay, 4 amps is a lot, but most things that produce heat, like your stove and so on, actually draw a whole lot of current. All you have to do is check to see how big the wire is that you're plugging into the wall. I mean, if it's a little tiny wire like this, you say, it's not drawing too much current. This thing's not going to heat up very much. But if you have like a space heater, a lot of times you go to plug it in, and it's this big fat cord because you want be able to have like a whole bunch of current to pass through it without much resistance, so it doesn't heat up and cause a problem. Anyways, we solved the problem. So I equals dq dt, or if we assume a constant flow, we can get away with delta q over delta t. Sir?
I can come see you later too, if that's better.
Yes, that would be okay. Thank you, sir. Wow. How's the retest coming? Am I distracting you? Okay. You're pretty proficient at ignoring me. That look. All right. So we say, okay, how much current? Delta Q equals I delta T. So we'll say 4 amps, 60 seconds. 4 times 60, 240 what? Coulombs. That's not what they asked for. They don't want to know how much charge went through. They want to know how many electrons went through. What are we going to do? So 240 coulombs divided by 1.602 times 10 to the negative 19 coulombs per electron. And yeah, there should be a negative sign in front of both of these, but, you know, don't worry about it, Stephen. We're just after the number. Wow. What'd you get, ma'am? I got like 1.5 times 10 to the 21. Uh-oh. Okay. So 1.5 times 10 to the 21 electrons. That'd be just a bit of electrons, right?
Just a dabble.
Just a tad. So that would be, see if I get this right. That'd be like 1,500 billion electrons. That's a lot
Well,
in 1 minute. That's beyond anyone's comprehension. Yeah. Okay. Next part. No. Current density. Okay, so you've got this wire. Wires are really kind of like cylinders of metal, but they're long and they're usually flexible because, you know, on our scale, the radius of the cylinder is usually pretty small and the length of the wire is pretty large, so they're usually fairly flexible and they're covered with insulators and so on. All set? All right. Any problems? Did you... Another A, another day?
Maybe.
Okay. Thank you. Have a good one. So, current density. It's kind of what it sounds like. If there's current flowing through this wire, okay, imagine looking at the cross-sectional area of this wire, kind of like a window that the current is flowing through. and we say current density, J, would be how much current flows per unit area. Okay, just like all our densities, it's always per unit length, per unit area, or per unit volume, because we live in a three-dimensional world. So this is kind of like how much current flows through a certain cross-section of our wire, and it's called the current density. Now, full truth between us. This doesn't cut it, because this works if the current density is uniform. Usually, in a wire, there's more flow of current on the edges than in the middle. Electrons hate each other's guts, right? Even if they were positive, they'd still hate each other's guts. So they move out to the outside of the wire, and the current density is actually greater toward the outside than toward the inside. So this kind of works as long as we use little tiny windows. So if I use a little tiny area and say, okay, what's the current flowing through that little tiny area? If I make it small enough, then we can say, oh, it's probably fairly uniform through that tiny little area. So what they do is they say, okay, for uniform current density, this equation is just fine. For real life, we have to do something a little different. Okay? We have to say, look, we're going to take teeny tiny areas. When we take that teeny tiny area, multiply it by the current density, we get a teeny tiny bit of the overall current. Add up the effect of all those areas, and we get the overall current in the circuit. So we have to define current density as an integral, breaking up the cross-sectional area into a whole bunch of little tiny windows. And each of those little DAs has going through it a little bit of current. And so we have to look at the current density that way. Now, every now and then in a problem, they'll say, oh, this is just fine. But in real life, we have to go that way. Okay? And that's all I have to say about that. Oh, except, what do you think the units are of current density? Amps per square meter. Perfect. Yep. No dead white scientists this time. We just call them amps per square meter. Okay. Next is something that really surprised me when I learned it way back when. And it's called drift velocity. Okay, remember a few minutes ago when we said there was like 1,500 billion electrons traveling through a heating element every minute. And you think, wow, that's a lot of electrons. So in a normal circuit, you've got a wire. Okay, we are going to make one side of it positive using a battery or some kind of energy source. This side negative, and current's going to flow. How fast do you think the electrons are moving in the wire?
Light speed.
You'd think really, really, really fast. I mean, if you're going to get 1,500 billion electrons through a heating element in 1 minute, they have to be like flying. If you pick up a landline and you call Europe and your voice is heard almost instantaneously on the other end, very small delay, those electrons must be cooking. The reality is exactly opposite. Electrons move very, 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 very slowly through. So I set up a wire and put a potential difference across it, and the electrons start to flow. The electrons flow at like 1/10 of a millimeter every second. Now, a millimeter is the thickness of a dime, so it's a tenth of the thickness of a dime every second these little guys are moving. You say, what? That doesn't make any sense to me at all. Now, a couple things before we get into the explanation of how that's possible. The electron actually has two velocities. It's random velocity. It's kind of like, an electron's kind of like a little kid on a whole lot of sugar. Okay? What he's doing, there's a lot of random motion. Pew, 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 pew. And that random motion is really fast. That's like 10 to the 6th meters per second. Okay? That's upwards around 600 miles an hour. Okay? But it's random. It's in all different directions. No matter what's going on with the battery, this random motion is just like everywhere, in every direction. But then there's this drift velocity. The electric field sets up this motion this way that just is very stately and moves everything to the right at about 10 to the minus 4 meters per second. Which I said is like a tenth of a thickness of a dime every second. So this motion, this crazy 600 mile per hour motion, is random, but it's all flowing gently to the right. So it's kind of like if we decided to take all our middle schoolers and ship them out of Granville. So we get all the buses we have, we fill them up each with middle schoolers, and we put them all on Wilson Avenue, and they start to drive down the road at 2 miles an hour. So inside the bus, pew, 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 kids are like bouncing off the walls and, everything's flying. But the bus is kind of like just gently moving down the street. And hours and hours later, we'd be free of them. But that's kind of what's happening. Now, if electrons move that slowly, how do we get 1,500 billion of them to pass through a wire every second? They gotta be small. Electrons. There's zillions of electrons in the wire, and they are smaller than we can possibly imagine. So when they do this, it's like billions of them have just gone through the circuit. Is that crazy? Reality is just so bizarre. People watch science fiction because they like, cool, weird stuff. This is really cool and weird to me. This is bizarre. Electrons are that small and that numerous that, move the whole lot of them 1 millimeter, and you've just sent billions of them through the circuit. It's like, that just blows my mind. Okay. So, how is it that if I have a landline, we don't use this too much anymore, but if I have a landline and I speak to somebody in Europe, my voice is there like now?
Because if you move one electron here, you're moving one there.
Right. If I take an electron here, this bunch of electrons, and just move them to the right a little bit, way down the line, they all just moved a little bit. So when you're sending that tiny current across the ocean, the electron next to you doesn't move very far. It's not like that electron has to zoom, shoot over to Europe and deliver your message. He's just influencing the next one, which influences the next one, which influences the next one. It's back to that ball in a tube thing, right? You got a long tube full of marbles. When I shove one in this end, one falls out the other end, even if the other end's in the parking lot, right? So the effect is almost immediate, but the electrons don't go very far. Just blows me away. It's just hard to imagine what's going on. All right. We're doing really well. Okay, so, excuse me. We imagine our wire is a long cylinder again. The total amount of charge available for conduction, we're going to call it delta Q. Okay. This number n, they define as the number of charged particles per unit volume. It's a little strange. Okay. Then we say the area of the wire is A, the length of the wire is L, so the volume of the wire is A times L. So this puppy right here represents the volume, and this little guy is the charge of one particle. Okay, so the only real new thing here is this funny little n, and that's not a Greek letter or anything, it's just normal n, and it represents how many charged particles are available per unit volume. So that's usually a really, really big number. Okay, now drift velocity is L divided by, we'll just use delta T like we normally do. So again, drift velocity is the speed of those buses on the way out of town. It's really slow and stately. It's just this motion that's superimposed upon this strange random motion, thermal motion of the electrons. Okay, so in that case, I can rearrange this guy and say that delta T is equal to L over the drift velocity. Okay, and now you can kind of see what I'm up to. Because if current is how much charge moves per unit time, I can say NALQ, that's my delta Q, divided by L over V sub D, drift velocity. Wow! Current is equal to, let me see, NAQ V sub D. So now we've got current written in terms of drift velocity. So if we think of current as how fast how much charge flows through every second, we can rewrite it in terms of the particles in the wire and their actual velocity, this tiny velocity at V sub D. All right, my apologies to those watching the video. I kind of ran out of room. I need to, before I erase this, I need to do one last step. We need to think about current density. Current density, therefore, remember, is the amount of current passing through A, the cross-sectional area. So it's not a huge leap to say, okay, current density then is N times Q times V sub D. Okay, remember V sub D is not voltage, that's velocity. Good old-fashioned how far you go in a certain period of time. So that's our equation of choice right there. J equals NQ V sub D. Give you a chance to catch up here. Okay, my notes say, take a look at the examples, Mr. Evelyn. So, ooh, this is a current density example. Okay. It says a copper wire carries a current of 10 amps and has a cross-sectional area of 0.050 square centimeters. Estimate the drift velocity of the electrons. It's like, oh, okay. Whoops. Let's get rid of that. There we go. All right. So they're telling us the current. They tell us the cross-sectional area. Now, down below, they give us some clues about N, because this is a really hard number to come up with. From the density of the copper, its molecular mass, and Avogadro's number, we can come up with a number of N of 8.5 times 10 to the 28 atoms per cubic meter. So if, for just a second, we assume that every atom donates an electron to the conduction electrons of the metal, we can give this a shot. We can figure out, okay, what's the drift velocity going to be? So let's see how this goes.
Do they always give you it like that?
Generally, or they'll give you enough information to figure it out. Okay. So we could back up one equation here and say that I is NAQ V sub D, and therefore V sub D is equal to I divided by NAQ. So if we're really conservative about this and say, okay, every atom donates one electron to the mix, we can say, okay, 10 amps, that's a lot of current. Down below, 8.5 times 10 to the 28. A cross-sectional area of, ooh, darn, I think we're going to need to change that over to meters squared. Any ideas? 0.050 centimeters squared. There's 100 centimeters in a meter, but we're changing not centimeters to meters, we're changing centimeters squared to meters squared. So in other words, we need to divide by 10,000. So it's like 0.0000050 square meters. Or we can just say 1, 2, 3, 4, 5, 6. 5.0 times 10 to the minus 6 square meters. So watch your units, please. And then Q, of course, let me get this out of the way. 1.602 times 10 to the negative 19 coulombs. All right, let's see what it yields us. All right, so I'm getting like 1.46, 2 sig figs. Yeah, 1.5 times 10 to the negative 4. Okay, super slow. 0.00015 meters per second. 10 amps of current, which is huge. That would heat up most of the wires that you use in your house. If you sent 10 amps through them, you would know that they had way too much current passing through them. Yet, the drift velocity, the movement of the electrons through the wire, extremely slow. It's just kind of weird. How you doing, Lucas? Is this making any sense? Okay. Everyone's kind of quiet.
If you like turned on this current and put it in a wire, eventually with that one electron that's actually moving that slow, be the one that would like pass through. You know what I'm saying?
No.
You're saying that that the electrons are moving like super slow.
Yes.
So let's say you have like a 10-foot wire, and they're moving at that speed. If after like a certain amount of time, with that specific electron that's moving that slow, be the one that would get to the end of the wire.
But they're all moving that slow. So there's billions upon billions of them doing this. So we're not talking about the motion of one electron.
Yeah, like you know how we talk about like if in case you're moving one electron and the other one is like it's like the marble thing. Like you push one marble.
Oh, I see what you're saying. Yeah.
But like is the marble that like you're pushing super slow, would that one eventually be the one that would fall out the end?
It could. It could. It might. I mean, if you turn on the heater or whatever it is, and you leave it on, it's possible for an electron to make it across the entire wire, but it's not necessary. It's the energy that we're moving from place to place, and the electrons are just carrying the energy. So it's just that there's so many of them that you can get a huge current, even though they move very, very slowly. And remember, they're not moving slowly. They're moving at like 600 miles per hour with random motion. So they're going round, backwards, forwards, up and down, all like just nuts at 600 miles per hour. Meanwhile, that motion, that crazy random motion, has superimposed on it this stately, very slow, glacial motion from one side of the wire to the other. Yeah. All right. I still have trouble imagining that. Let's do that. Okay. Another current density example here. And unfortunately, I didn't leave myself a whole lot of room to write here, so let's give this a shot. All right. We are just about done. I'm not sure we'll get through this one. Let's just set it up, and we'll call it good, and we'll move on to the next hour. In fact, we just have a couple minutes left, and you're going to take a test. No, you have first hour first, and then you see me. The magnitude of the current density of a certain cylindrical wire is given as a function of radial distance from the center with an equation of B times R. R is in meters, J is in amperes per square meter, and B is like this constant. Okay, so in English, what does this mean? We've got this wire, and if you start at the center, where R equals 0, the current density is 0. Because when R equals 0, J equals 0, according to our little equation here. But as R gets bigger, as you move further out, the current density gets bigger and bigger and bigger. So that more closely approximates reality. That if you got a big, thick wire, most of the charge is moving along the surface of the wire, not as much through the interior. Okay? So they give us the constants and everything, and they say this function applies to the wire's radius of 2 millimeters. So $2-millimeter radius of wire. How much current is contained within the width of a thin ring concentric with the wire if the ring has a radial width of 10 micrometers and is at a radial distance of, okay, so what they're asking here is, if this is the wire going into the board, how much current is going through, say, that much of it? Okay, we won't have time to finish it, but remember, we say, okay, current is the integral of J dA. We can also say, if we get rid of the integral for a moment, we can also write this as a differential equation. Okay, a differential equation would look like this. dI, a little tiny bit of the current, is equal to J dA. So this is what they're after. They're saying, how much of what tiny little fraction of the total current is going through this concentric ring given those parameters? Okay? We'll take a look at this one next time because we are just out of time. So we made a really good start to the new unit. This stuff isn't terrible. This problem sounds terrible, but it's not. And so this first chapter, chapter 26, we're going to kind of fly through. And then chapter 27, we actually get into actual circuits. And that's a little bit more fun. So we're getting the introductory stuff out of the way.